So this is an introductory lecture to the linear regression model, or what we often write just the LRM. The starting point for the linear regression model is a random sample. We have two variables, x variable and a y variable, and we have n observations. So we have n pairs, y1, x1, and so on. So to give you a concrete example to consider in the lecture, let's say that the x variable is the number of hours that a randomly selected student studies for an exam, and yi is the result or the score on the final exam. Here's an example where n is equal to 9. That means that we are dealing with 18 random variables. And before I do the experiment, they are just indeed random variables. We don't have any numbers then. Note that econometrics doesn't tend to make a distinction between upper and lower case variables, such as we do in probability theory sometimes. So x1 will denote the random variable x1 as well as the actual value that's observed after the experiment. It's a random sample, so this random variable here will be independent of that random variable here. The amount that the first student studies will be independent of the amount that the second student studies. The same goes for, let's say, y1 and y2, the result on the exam for these two students. And of course, even if you do x1 and y2, they are independent. But these two are not independent. X1 and Y1, there is a clear dependence, at least that's what we believe. The amount of hours studied will affect the result on the final exam. So we simply assume that each one of these X random variables have some given distribution. Don't know what it is, but they are identically distributed, have the same distribution, which means that they have the same expected value, the same variance. The same is true for the y random variables. They are all drawn from a different distribution from the x's. So then we perform the experiment under these assumptions. x1 will take a value, y1 will take a value, and so on. And let's say that this is what we observe after the experiment. So the way you should view 109 now is that that is a drawing from the random variable x1, and similarly for the other numbers. So that's the setup, our random sample. Based on this random sample of two variables, we can formulate the linear regression model. And the linear regression model assumes that there is a relationship between these two variables of a very specific kind. And the relationship is this. It's assumed that the yi random variable, in our example, that's the result on the final exam, is related to the xi random variable through a linear function, beta 1 plus beta 2 xi. So beta 1 is the intercept, beta 2 is the slope, plus epsilon I, where epsilon I is an error term. So the idea behind this particular specification, or this assumption, is that the y variable is partly determined by the x variable, and it's partly, or I should say, and this part is linear in the linear regression model. That's where the term linear comes from. So to some extent, the y variable is determined linearly by the x variable. The result on the final exam is determined partly by the number of hours that the student studies. and it's determined partly by the error term epsilon I. You can think of this error term epsilon I as everything else that determines yi in addition to the xi variable. And those are things that we have not measured. For example, if this is a course in econometrics, then the result on the final exam could depend on, in addition to the number of hours that the student studies, the amount of mathematics that the student has studied before entering the course. But it can contain a lot of other things, such as could contain like the intelligence of the student, for example. Anything that you believe affects the result on the final exam can be contained in this error term. The error term is the reason for why two students who study exactly the same amount, so that beta 1 plus beta 2 xi is the same, will typically end up with different results on the final exam. They are simply, in the notation of econometrics, hit by different error terms. Notice that the variable that we put on the left-hand side is the y variable. That's very common notation in econometrics. The variable we put on the right-hand side will be the x variable. And the idea here is that there is a link from the x variable to the y variable and not the opposite. The amount of hours you study determine, at least to some extent, the result on the final exam, but the opposite cannot be claimed because that would sort of going backwards in time. So that y variable is for this reason called the dependent or the explained variable. That's the variable we're trying to explain. Trying to explain the result on the final exam. It's dependent because it depends on the x variable. The x variable, on the other hand, is called the explanatory variable because it's trying to explain the y variable. Sometimes it's also called the independent variable, simply because it doesn't depend on anything in this setting. Like we said, epsilon I is called the error term. Try to never call it the residual term or the residual, because we have already used that concept for the deviations from a trend line. The symbols beta 1 and beta 2 are, in this setup, unknown parameters. The whole idea of the linear regression model is that I believe that there is this relationship between y and x, but I don't know the exact relationship. I don't know what the intercept and the slope is, but I'm willing to assume that there is a linear relationship between x and y. So to state this again, I just repeated the specification for the linear regression model. So we assume that the y variable is explained partly by the x variable. And it's done so through this linear expression, beta 1 plus beta 2 xi. But it's also partly undetermined. So there is an error term that also influences the y variable. So looking at the expression for the linear regression model, the y variable, yi, and xi are viewed as random variables, while beta 1 and beta 2 are viewed as scalars, or just unknown constants. The error term, epsilon I, well, if we move beta 1 plus beta 2 xi to the other side, we see that the error term epsilon I is yi minus beta 1 minus beta 2 xi. So that's just simply a function of the random variables y and x. And that makes the error term a random variable itself. So in this model, you should also view the error term as a random variable. Whatever affects the y variable in addition to the x variable is something random. But there is an important distinction between them, and that's the fact that since beta 1 and beta 2 are unknown, we don't know them, epsilon I, the error term itself, will be unobserved. That is, even after the experiment, I have no clue what the actual outcome of these random variables were, simply because these beta 1s and beta 2s are unknown parameters. So after the experiment, I observe yi and xi. I do not observe and I do not know beta 1 and beta 2 constants, and I do not know the outcome of the error terms epsilon I. So here is sort of the whole point of specifying the linear regression model. I observe data. I observe data on an x variable and I observe data on a y variable. I need to commit in the sense that I need to specify that I believe that there is a relationship from the x variable to the y variable. Once I've done that, I can make the linear regression model assumption. So I'm simply assume that y is partly determined by x linearly and partly determined by an error term. The focus of my investigation is the deterministic part. So the focus of my investigation is to try to figure out estimates of beta 1 and beta 2. So I'm basically trying to see through the noise created by the error term to reveal this underlying deterministic relationship between x and y. So in later lectures, we'll see exactly how we can do that, how we can find estimates of beta 1 and beta 2 based on our observations